Good morning, everybody. Let me finish getting situated. All right. So, like always, can I get someone in the voice chat to acknowledge my existence and say hello? Awesome. Thank you, Esteban. All right. So, and thank you, Cody. Let's see. Welcome to the last class day that we have, right? The only thing after this is the last lesson. Everything after today is just review for exams and exams. So we'll have a review on Friday. We'll have the third midterm on Monday. Then you have Thanksgiving. And then that Monday and Tuesday after Thanksgiving, we're going to have a review for the final exam. So this is it, man. We've reached the end of the semester practically. So are there any questions, comments, or concerns before we get started today? All right, in that case, let's go ahead and get going. Today's going to be a lot like the last class. Oh, which, by the way, don't forget, if in case you haven't noticed, let me... it should be available on Blackboard. I also posted it here. I made a Quizlet flashcard deck from the questions on the exam. They're not always one-to-one questions, but I basically sat down and I'd write a question in the exam, and then I'd have the screen open, and I'd write I'd make a flashcard that was basically the same stuff. So go take a look at those. If you feel strong about all of those, like 60 flashcards. Oh, and the exam is, I know we originally stated it was going to be 65. Ended up only being 60 because 65 is a lot of questions, and I got to 60, and I was like, all right, that's enough. But it'll be the same amount of time. But yeah, but if you go follow that link that's on Blackboard, do those flashcards. We will do the flashcards kind of together in class on Friday, but if you feel strong about that, you're going to do just fine on the exam. And then the final exam, which of course is optional, will be the exact same structure. I'll make a bigger flashcard deck that kind of reflects the questions on the final exam. So, any questions about that? Thank you for typing nope, Esteban. You're welcome. Hopefully that should be a pretty good study aid, as they say. All right, so let's dig into today's lecture. We're going to talk about state tables and graphs. And again, we're kind of just going to look at some sequential circuits, do some analysis, kind of like we did last time, and sort of build our way through. I'll wait and see if Adrian has a question before we get started. I'll stop typing. Can't start typing and then give up.
Just use your mic.
Or just use your microphone, yeah.
Mic.
Apple makes a good hardware product, Cody. Like, there's no
I'm running
debating that, man.
Mac VM on my computer right now.
Yeah. But now, you buy a good PC right now, it's going to last you like 2 years. You buy a Mac right now, it's going to last you like 10 years. I've been using the same Mac since 2014. Adrian asks a real question. Should we study anything else besides the flashcards? I agree, Carlton. The Mac terminal is essential. Also, Mac is Unix-based, which makes everything a whole lot easier. If you're a CS major, you should not be using Windows. You should be using Linux or be using Mac. Then I can't help you, Cody.
If I don't use Windows,
If you're a W, then you just shouldn't be using a computer at all.
how am I supposed to see out my car?
Devin, I love you, man, but your mic is terrible.
It's Wi-Fi.
Or your Wi-Fi is bad too, yeah. So you sound like you're broadcasting to us from the moon in 1965. All right. So we can argue about Macs versus PCs later. It's not really an argument. Mac is a superior product. I say that as I'm using Windows right now. But let's talk about transition, otherwise known as state tables. So we've already seen, let me click through some stuff. We've already seen transition tables for small sequential circuits. But to design a larger sequential circuit, we need a more systematic approach, right? Kind of like way back in the day when we were looking at Boolean algebra simplification, we needed a sort of process to kind of streamline things a little bit and make it a little bit more algorithmic, a little more systematic. We're going to kind of do a similar thing here with our sequential circuits. So let's see here. The transition and state tables for a sequential circuit specify, here's a definition. The transition and state tables for a sequential circuit specify the next state and the output of the circuit in terms of its present state and input. The following method can be used to construct transition tables. So we're going to work through each of the steps one at a time, and we're going to use this circuit as an example. We can see here that it's a Moore type machine, right? It's a Moore because the output is only dependent on the flip-flops. In fact, I think this is the same machine that we used in the last class. So we're going to kind of clock our way through and work out everything. So step one here, determine the flip-flop input equations for the circuit, right? So that would be, our dA equals something and our dB equals something, right? We need those flip-flop input equations, right? So dA here is equal to what? X, our input X or B prime. And our input dB, or excuse me, our flip-flop input equation, dB is X or A. So, pretty straight up, you just look at the flip-flop inputs and you say, well, what are the equations? That's step one. Any questions about that? All right, so from there we move on to step two, which is derive the next state equation for each of the flip-flops from its input equations using one of the following relations. So we saw this a little bit last time when we looked at, we had JK flip-flops and we had to deal with their input equations. But here you can kind of see a listing of all of the different types, right? A D flip-flop, with clock enable, a T flip-flop, an SR flip-flop, right? So if this is our input equation, then those inputs are going to tie. So this is, for, let me scratch that out and just say for A plus, that's going to be equal to dA for a D flip-flop, right? And B plus is going to be equal to dB. Just like that. So you're going to tie your flip-flop input equation to your next state equation based on the type of flip-flop that you're using, or that is given to you, rather. All right, any questions about that? See, Adrian's typing. All right, Adrian asks, in a D-CE flip-flop, when it is transparent, how would D react and would it resemble Q? Yeah, so I mean, you can sort of see that here in the definition, right? If CE is true, right, if C equals 1, then it's just a transparent regular D flip-flop. But if CE equals 0, then the state doesn't update, right? And it just feeds the present state back to the next state. So yeah, so when CE equals 1, it's just going to be a regular old D flip-flop. Did that answer your question, Adrian? Cool, no problem. All right. So let's move on from that. So in our example, we are working with D flip-flops. So this is the way it's going to be, right? We already wrote this down, but we're going to say it again. That A plus is equal to dA, which of course is equal to what? X or b prime. And b plus is equal to db, which is equal to x or a. So there's our next state equations. Oop, almost cut myself off. Let me write that out. Next state or characteristic equations. All right, so, see Cody's typing. Okay, so for the DB flip-flop, it has an OR gate. Oh, you're absolutely right, because I'm dumb, man. That's why. Because that is an OR gate, which means it should be X or A. Let me roll back here. Or A. Good catch, Cody. Because I was just rushing. I wasn't really paying attention. All right, so everybody see that difference there? That's an XOR gate, but that's just an OR gate, so it's A, X or A. All right, step 3, plot a next state map for each flip-flop. So here is where it gets kind of cool. We're gonna sort of take our equations. Let's see, we had what? A plus is X or B prime. Now, to put it in the map, it needs to sort of be that normal form, right? So it's going to be X, what? So X and B, right? Because it's going to be X and B prime prime, or X prime and B prime. So it's going to be X, B, or X prime, B prime. And so we're going to go ahead and drop those values into this equation, right? So X and B, X is 1, B is 1, right, is these guys. And then X prime, B prime, X is 0, B is 0 is going to be those guys right there. Does everyone see what we're doing? We're just doing that reverse engineering of the K-map like before. Now B plus is X or A, not X or B, A. And let's see, so now it gets kind of strange, right? So we have X, which is just X equals 1, which is going to be this grouping. And we have A, which is A equals 1, is going to be this group of 4. So, any questions about how we reverse engineer the K-map? And we'll see why here in just a second. All right, so let's go to the next one, right? So we take this, and now step 4 is we're going to combine these maps to form the state transition table. So what we're going to do effectively is sort of set up the left-hand side, right? What is the present state? AB, 0, 0, 0, 1, 1, 1, 1, 0. And then here we're going to set up the next state, right? A plus B plus, which is going to have the same structure, but we're going to consider it for X equals 0 and X equals 1. So if we look just at A plus, and we look just at X equals 0, right? That's this column of the K-map, right? So it's 1, 0, 0, 1, right? Notice that AB is also written in that gray code, right? 0, 1, 3, and 2. So for X0, we just basically see all of the columns for each one. So 1, 0, 0, 1. And then for B plus at X equals 0, that's 0, 0, 1, 1. And so we get 0, 0, 1, 1 as well. And we do the same thing for X equals 1, right? For A plus, that's 0, 1, 1, 1, 0, 1, 1, 1. And for B plus, that's 1, 1, 1, 1, all the way down. 1, 1, 1, 1. All the way down. And then, of course, the outputs here, remember Z was equal to what? A XOR B. And that's coming from here. So 0, 1, 0, 1. So we just put together our table from what we see in the K-maps. Any questions about that? It's pretty straightforward, right? The K-map just sort of is the columns. So all I have to do is look at it and copy stuff over. Now the next thing, so this is the transition table, and this is an important definition that is on the exam. So the transition table is the one that has everything listed out in binary notation, right? 0, 0, 0, 1, 1, 1, 1, 0. The difference between a transitions table and a state table is the state table replaces that binary notation with state labels, right? So now we have, 0, 1, 2, 3 for S0, S1, S2, and S3. And then what are the values here? S3, S0, S1, and S2, right? Because we want to tie it to the state. We don't necessarily want to be all about the inputs themselves. So let's I'm going to kind of toggle back and forth here, right? So if this is S0, S1, S2, and S3, or excuse me, S3 is up here, this is S3 and S2. Right here we're saying that this is S2, S0, S1, and S3, right? So the idea is that if we are at x equals 0, and we are currently at state 0, then we will go to state 2. Well, that doesn't make a lot of sense. Hold on. Oh, I see what they did. Okay. Hold on. I'm going to erase some stuff. So they did a thing here that I kind of disagree with, but we're gonna go with it. Because they've labeled ahead of time. They've said, instead of tying them to the numbers directly, they've said that 0, 0 is state 0, 0, 1 is state 1, but 1, 1 is state 2, and 1, 0 is state 3, right? So they've broken away from tying them directly where 0 is binary 0 and 1 is binary 1, right? The oddball here is that state 2 is 1, 1, and state 3 is 1, 0. Cody asks, is that a standard operation? And the answer is kind of, because it is kind of arbitrary, right? So remember way back at the beginning of the semester, we talked about, when you encode things, or if you, sort of agree on a specific convention, you can do it pretty much arbitrarily. You can do whatever you want as long as you sort of agree on what you're doing. And so here they've just defined, they've said 0, 1, so this gray code sequence is still going to be 0, 1, 2, and 3. So now we have x equals 0, going from 0, 0 to 1, 0, and that means that it's going to be state 3. Then if you're at state 1 and you get a 0, you're going to go to state 0. If you're at state 2 and you get a 0, you're going to go to state 1. And if you're at state 3 and you get a 0, you're going to go to state 2. All right. So they just sort of arbitrarily decided that those were going to be the states. Now let's take a look over here at x1. So if we're at state 0 and we get a 1, that means we're going to go to state 1. If we're at state 1 and we get a 1, that means we're going to go to state 2. If we're at state 2 and we get a 1, well, we're going to stay at state 2, actually. And then if we're at state 3 and we get a 1, we're going to go to state 1. So the important thing is that they've labeled, or we have to recognize that they've labeled state 1 and, or excuse me, state 2 and state 3 sort of flip-flopped from what they would be in binary. So that's why we see this guy here, right? That's 0, 0, 0, 1, 1, 1, 1, 0, and then everything corresponds. So I know that was a little bit confusing, but are there any questions about that? All right. Now, once we have a state table, we can then put together what they call a state graph. A state graph contains the exact same information as the state table, but it just does it sort of in graphical form. So let's kind of take a look, right? So you have our boxes for state 0, state 1, state 2, and state 3. And then notice here below we've got whatever the output is at that state, right? So if we're at state 0, then our output is 0. If we're at state 1, then our output is 1. If we're at state 2, then our output is 0. And if we're at state 3, our output is 1, right? So that's our present state. And that's our output Z. And then here we see it sort of graphically defined. So if we were at state 0, and we get, so if we're here at state 0, and we get a 1, well, that means we go to state 1. So you can see the line that goes from 0 to 1 with the number, that's our x value, right? So that would be x equals 1. And that would be our x equals 0. All right, so if we're at state 0 and we get a 0, then we go to state 3, right? That's what we see here in the table. So we're basically just taking the information and sort of plotting it graphically. And the important things to remember is that's the present state, that's our output Z, and then we have these lines coming off based on whatever the input is, right? So that's x equals 1, and that's x equals 0. So if we're at state 3 and we get a 1, that means we're going to state 1. All right, any questions about deriving the state graph from the state table? It should be pretty straightforward. All right, in that case, let's go ahead and work out just one more example. We're going to take a look at this guy. This is that Mealy machine that we've seen before, right? We're going to determine the flip-flop input equations and the output equations from the circuit. So let's do that first, right? So we've got a number of different equations that we've got to work with here, right? We've got JA, KA, KB, and JB, right? So we've got, let's do them. JA is just equal to what? X and B. And KA is equal to X and JB is equal to X and KB is equal to X and A. And then down here our output equation is Z equals XB prime or XA or X prime A prime B. So now we've got our flip-flop input equations and we've got our output equations. So any questions about this first step in this example? All right, moving right along. So step 2, derive the next state equation for each flip-flop from its input equation using one of the following relations, right? So we're using JK flip-flops. I've gone ahead and copied over our state equations here, which means that we're doing this business. So that means that A plus is going to equal what? Well, let's just lay everything down. It's going to be J A prime or, let me say this, JA and A prime or KA prime and A. Now we need to fill in some of our stuff. So JA is equal to, so it's X, B, and A prime, or X prime and A. So a little bit of rearranging there. We're going to have A plus. I'm not going to have space for, so it's going to be X, A prime B or X prime A. And we'll see the similar thing for B plus. Should be JB, not A. So JB B prime or KB prime B means that B plus is going to be equal to XA B prime or X prime B. Make sure I got that right. Right, they're both. KB should be XA. So let me fix that. It feels wrong. Feels wrong, man. So KB prime, that means it's going to be X A prime. Nope. X A prime and B, which means that we still need to get it into sum of products form, right? Because the next thing we need to do is plug it into our K-maps. So I'll need to expand this out a little bit. Say X prime is equal to XAB prime or what do we have? So that's going to be X prime or A prime B. Hold on. Oh, did I get it backwards up there? That's what I did. Guys are on point state. Let's see. Okay, so some of this stuff is screwed up. I get this backwards. So we get for copy and pasting. So let's say we're going to ignore all of that. So JB is just X. So now let's reassemble it. B plus. Hold on, let's take a deep breath. Let's make sure we can screw anything else up. JB is X. KB is X and A. JA is XB. KA is X. Okay. So, so JB, that's going to be X, B prime, or, well, I guess that's what we had before, X A prime, B, so B plus is going to be X, B prime, or X prime or A prime B, meaning after all of that, B plus is going to be X B prime or X prime B or A prime B. All right. So, unless I've made any more mistakes, there's our first equation. And our second one. I see Cody is typing. Cody asks, could you simplify that at X, X or B, or A, B, or not A and B? You could, but you wouldn't want to, right? Because the goal is we need it in product of sums because we need to put it into our K-map again. So you want to leave it just the way it is. All right, so now let's go ahead and take a look at that. Let me grab these equations and kind of copy them over. So A plus is equal to what? X A prime B or X prime A B plus is XB prime or X prime B or A prime B, and then all the way back, Z was something, XB prime or XA or X prime A prime B. All right, we have a different color. Let me grab like green or something. Okay, so let's do A plus first. All right, so here we have what? X A prime B should be X is 1, A is 0, B is 1. So that's that guy. And then X prime A is going to be X is 0, A is 1, which is going to be that guy. Then going over to B plus, we've got what? X and B prime, so that's going to be X is 1, B is 0, so that's going to be that business like that. Then X prime B, so that's going to be X is 0, B is 1, so that's going to be that guy. And then finally we have A prime B, so A is 0, B is 1, and that's going to be that guy. And then going over to Z, we got X and B prime. That's going to be X is 1, B is 0. So that grouping. Then X and A. Let's see. X and A is going to be... Where's X and A? Oh, it's going to be these two. And then X prime, A prime, and B is X is 0, A is 0, B is 1. And that's going to be that guy. Now from there, we should already kind of know what's going to happen. If we could, I'm going to do it right like over here in the corner. I'm going to say if we have A and B, it's going to be 0, 0, 0, 1, 1, 1, and 1, 0. And if we have X equals 0, A plus, B plus. So for X equals 0, that's going to be 0, 0, 1, 1 for A plus 0, 0, 1, 1. And let's see, B plus for X equals 0 is going to be 0, 1, 1, 0. So 0, 1, 1, 0. And then for X equals 1, A plus B plus is going to give us, let's see, 0, 1, 0, 0. And B plus is going to be 1, 1, 0, 1. And then let's see, Z is actually going to split up. I'm going to bring it over here and say for Z, we have different Z's for if X is equal to 0 and X is equal to 1. And that's going to be 0, 1, 0, 0, and 1, 0, 1, 1. So, any questions about how we derived sort of these columns using our K-map from our characteristic equations? Okay, all right, so let's see. Step 4 then is do what we just did, combine these maps to form the state transition table. And you can see, if you go back and look at the annotations, it does line up. And so now what we'll do is we'll kind of build our state table using the exact same method, right? So remember now we're going to stick to this convention, S0, S1, S2, and S3. Which means that here is 0, 0, so that's going to be state 0, State 1, look, it's going to stay exactly the same. Means if x is equal to 0, the state doesn't change. Oop, S2 and S3. But if we have x equals 1, then we have go 0 goes to state 1. State 1 goes to state 2. State 2 goes back to state 0. And state 3 goes to state 1. So 1, 2, 0, and 1. And then x, of course, is x. And if we see what they gave us, that's what we got here, right? So if x is equal to 0, then the state never changes. And if x goes to 1, then the state progresses along that thing. 0 goes to 1, 1 goes to 2, 2 goes to 0, and 3 goes to 1. And then the output is what the output is. Any questions about how we derived this table? All right, in that case, from there, we can look at the state graph here. Now, it's a little bit of a different notation, and that is based on the state. So we have our states here, S0, S2, S1. Remember now that since it's a Mealy machine, right, output also depends on the input. So we have what state we're at, and then what the output is going to be, what the next state is going to be. So if we look at S0, we see here that we've got 0 and 0. So the first graph, let me see, S1 and 0. Okay, so let's see. So we've got S0. Hold on, I'm going to look at one thing. What am I doing? S1, 0 to 1. Yeah, okay. Just want to make sure I wasn't going to screw that up. The top bar is the input, and underneath is the output, Z. So here we have S0. If the input is 0, it's going to stay at state 0, and the output will be 0. But if S0, if we're at state 0, and the input is 1, then we're going to go to state 1, and the output is 1. And if we go back and take a look at that, so if S0, if we're at state 0, and the input is 1, we go to state 1, and the output is 1. So it matches up. And then if we're at state 1, and the input is 0, then we stay at state 0, and the output is 1. But if we're at state 1 and the input is 1, then we go to state 2, and the output is 0. And so that's the structure, right? We have the state in the bubble. The arrow shows where we're going on the input. The notation here is input x crossed with z for each one. So any questions about that? Cody asks, is there any significance that the machine can't achieve state 3 when x equals 1? No, I mean, this is sort of an arbitrary state machine. So if this was designed for a specific application, then yeah, there might be some significance there. But the reality is, no, it's just an arbitrary example. Just happens to shake out that way. We also don't seem to be able to get to state 3 ever, right? In fact, yeah, there is no, if we go back and look at the table, if we're not already at state 3, so if we were to just look at the top ones, there's actually no way to get state 3. Yeah, that's kind of a peculiar example, but, you know, there are reasons for that. Maybe when you know, state 3 might be, if we were to map this onto some kind of, you know, pretend scenario, right? Maybe state 3 is like the reset. You turn it on, it loads into state 3, and it will stay there, right? As long as input is equal to 0, it's going to stay there at state 3 forever until you hit it with 1, and then it sort of goes through the clock, like it sort of clocks through this graph. So maybe something like that. But again, like I said, it's just an arbitrary example. All right. So real quick, let's just go ahead and recap that procedure for getting, basically the goal is to get to our state graph. Step 1, determine the flip-flop input equations and the output equations from the circuit. Look at the circuit, see what those equations are going to be. Then you derive the next state equation for each flip-flop from its input equation using the correct flip-flop relation equation. You know, if it's a D flip-flop or an SR flip-flop or a JK flip-flop, use the correct equation. Step 3, use those equations, plot the next state map for each flip-flop. So, you know, plot that on the K-map using that reverse engineering technique that we talked about. Then step 4, combine the next state maps to form the transition table. And then 5, derive the state table from the transition table, right? S0 through 3 or whatever on the left-hand side. Copy everything over. And then step 6, draw the state graph from the state table. And that is all there is to it. Any questions about that? All right. Well, in that case, if there are no questions, then we have reached the end, my friends. So there we go. And that is it for the lecture material of this course. Congratulations for reaching the end. And let's see. Like I said, on Friday, we will review for midterm exam 3, which will be everything that we've talked about since the last exam. Then on Monday, of course, you'll take it. That'll be online. There won't be any class on Monday. You're just going to take the exam online. Using the link on Blackboard. I'm using a different service to sort of proctor the exam. It's not Proctorio or anything. But you'll find the link to the exam in Blackboard when the time comes. Take the exam. It'll report the stuff. It should work out just fine. Then you'll have Thanksgiving. Then we'll review. Come back Monday and Tuesday after Thanksgiving. Monday and Wednesday after Thanksgiving. We'll review for the final exam. And then, of course, on Thursday, the final exam will be available. Esteban asks, where is the Quizlet? It's on Blackboard. And also, if you scroll up in this chat, it's up there somewhere. So go find it. It's in the exams folder on Blackboard.